Hello everyone and welcome to today's Bio-IT webinar. Rescale is excited to host today's webinar alongside MSTAR Simulations, where we'll be discussing with you accelerating biomedical innovation with digital R&D and focusing on future trends in large-scale design exploration, digital twins, and AI and ML. My name is Eric Muir. I'm a solutions architect at Rescale, and here at Rescale we are empowering scientific and engineering breakthroughs by eliminating the complexity of big compute and harnessing the near infinite power of a hybrid cloud infrastructure. I'm also joined by John Thomas, who's president at MSTAR CFD, and he will be introducing himself further a little bit later in today's webinar. Just a quick rundown of the agenda for today. First, I'll introduce the topic digital R&D. What do we mean by this term? What do we see the current trends, and where do we think the future is in terms of digital R&D? Next, I'll pass things off to John, who will be discussing the MSTAR CFD solver, which is really exciting in that it leverages GPU compute and the advances in the new architectures and algorithms enabled by GPUs to perform simulations at near real time. So John will be giving you a little bit of background on the theory of the CFD solver and then also showcasing some applications of the CFD solver in a digital twin application. Finally, I will continue the conversation by picking up on some of the other trends such as large-scale design exploration and applications of AI and ML in the biomedical industries. And then finally, I'll be presenting Rescale's take on a modern HPC experience where we are able to provide an environment and harness the near limitless compute available by today's cloud environments to accelerate scientific and engineering breakthroughs. So digital R&D, what is it? What do we mean by it? And where are we at with it today? So everyone is likely familiar with, the trends that simulation and computation have taken in the engineering and science world over the last several decades. Obviously, we first started all with physical experimentation, and then with the advent of computers, quickly harnessed the physical simulations that were capable to do very macroscopic computations and predictions of the physical world. Now, of course, over time, our abilities to do these simulations at higher fidelity and shorter timescales led us to today's current state, where you can get pretty darn accurate with the types of simulation that you're doing, as John will discuss. But there's still an inherent limitation to the scale and the time that you can do these simulations, where that limitation is oftentimes the infrastructure from which you're doing the computation. And so looking forward, we are seeing some new trends that when you kind of unleash the scale of a cloud infrastructure for computing, then it really lends itself to new capabilities that can accelerate the innovation in the biomedical worlds. And so specifically, we're looking at topics like digital twins, where you're able to have, a near exact replication of a physical entity in simulation. You're able to reproduce experimental results accurately in simulation, and then you're able to use that simulation to further expand in the design space and make improvements digitally without the expense and the time associated with physical modifications. This lends itself well to discussions around large-scale design exploration, where we're looking at scale of computation, not linearly where you do one simulation after another, but instead you're able to do hundreds and thousands of simulations in parallel, all at high fidelity, to ultimately arrive at a very optimal design. And then finally, we come to a new trend that I'm sure everyone is aware of, and that is AI and ML. And you can see examples of the new capabilities in multiple industries that AI and ML have produced. And so in today's discussion, we're going to focus more on how can these statistics-based algorithms and data-based algorithms be leveraged alongside the physical simulations that we're able to perform today, and really augment and be used to accelerate innovation and the design timeframe. And what's really interesting about AI and ML is it actually has such a unique and different computational requirement compared to what's more typical of physical simulation, and namely the use of GPUs, but also the need for large scale data integrations. And so when you look at the portfolio of these three topics, digital twins, large scale design exploration, AI and ML, it's apparent that in order to harness and leverage these new technologies and put them to work to improve our ability to innovate, we need a modern compute environment to go along with that. Pass things off to John, who's going to again discuss some exciting new breakthroughs and work that his team is doing with their MSTAR CFD solver and applications to digital twins.
Hi guys, my name is John Thomas. I come from MSTAR Simulations, and I'll be picking up this topic of accelerating biomedical innovation with digital R&D and talking about how important advances in both algorithms and architectures allow us to do things today in terms of simulation and digital twin modeling, etc., that we couldn't do just a few years ago, and talk about how these new advances parlay into machine learning and AI type algorithms. So my talk today is pretty straightforward. I'm going to be talking a bit about some of the theory and background behind numerical modeling and digital twins. So we're going to have a few slides here of theory, a few slides of math. Bear with me if you don't understand it. If you do get it, you'll know exactly what I'm talking about, of course. But I need to introduce where we're coming from a technical standpoint. I'm then going to jump right into examples of digital twins in action. You know, how we're using these things in the biopharma community. How they can be applied to your workflow, how they work with modern architectures to make hard predictions happen easily. And then we're going to talk about why we believe them, how we validate them, how we convince ourselves the physics they're predicting are true. And then I'll jump into next steps in terms of where this goes and what other opportunities we have to us in this space. So let me begin by talking about some governing equations and talking about some of the rules of the road here. So when we're talking about processes, fluid mechanical processes, reaction processes, bioreaction processes, etc., what's neat about all these processes, if they're fluid mechanical, that is that they're all governed by the same governing equations. That is, whether you're putting peanut butter into a jar, agitating a bioreactor, stretching some sort of viscous fluid, or using a twin screw extruder, all of these physics, as it were, are described by the same governing equations of momentum transport, conservation of mass, and conservation of species. And so if we can solve these equations appropriately, we can predict just about any fluid mechanical transport process, any sort of bioreactor behavior or mixing process of interest to us. But there's the rub. It's hard to solve these equations efficiently and be able to predict arbitrarily complex process outcomes. So within the context of these equations, and I'll focus here on the NavierStokes, which was the conservation of momentum, and a lot of folks have probably seen this. Our most common approach for solving the NavierStokes is to, well, break it up into little bits and then use the computer to solve how the velocity field and the pressure field vary across the domain. This is what a lot of CFD tools do. A lot of users spend their time making a mesh upon which they're going to solve these equations. And from these codes, we typically get a steady state representation of the time averaged mean flow field. What's important to recognize here is that we don't just have to start by discretizing the Navier-Stokes equations to predict these complex transport fluid mechanics. In the last decade or so, we've discovered new algorithms and new approaches for more efficiently solving these classical transport physics problems. Said again, these canonical relationships, conservation of mass, energy, and momentum, they are still true. They are still valid, but we can come up with alternative strategies for solving them that are a bit more efficient and a bit better tailored for modern HPC. Let me talk about this in a bit more detail. When traditionally solving these equations to predict how these fluids move and how the vessels react and whatnot, We typically start with the NavierStokes equations, break the system up, and for those who may be mathematically inclined, into a sparse diagonal banded matrix. We relax this matrix to minimize residuals to predict some sort of mean flow field. We typically get the steady state flow behavior. We try to be judicious about how high resolution we go because of the problem scales unfavorably with system size, owing to the fact that it's this banded matrix. It's certainly practical to parallelize this process, and you can run standard CFD tools across hundreds of thousands of CPUs if you want to. If we use alternative approaches, such as the Boltzmann transport equation to solve NavierStokes, things change. To begin, we no longer have these large, sparse banded matrices. We just have array operations. The algorithms become inherently transient, and because each local operation is so simple, we can easily handle lattices containing hundreds of millions to potentially billions of lattice points. And again, because we're doing array operations that are fully localized, the parallelizability is the software is trivial to parallelize. What that means is that it goes hand in glove inside modern HPC architecture, such as GPUs and whatnot. So again, although we have two ways of solving the same equations as we're predicting the same fluid mechanics, when we recast this problem into a problem that can be solved using the Boltzmann transport equation, we can take advantage of modern architecture that make this complex physics much, much easier to solve. Let me talk about that in more detail. When we use these Boltzmann-based approaches on GPUs, we move away from performing a calculation and predicting a mean flow field, as it were, and towards doing a numerical experiment. So again, what we get out of these simulations is an actual process. We're watching the fluid mechanics evolve in front of us. Here I have a pitch blade impeller agitating an unbaffled tank leading to a vortex, as it were. We're watching that vortex evolve in space and time in response to the motion of the impeller. And here I'm colorizing one slice through this tank per velocity, as it were, and showing the free surface is somewhat transparent. Here I'm adding fluid to a slowly spinning agitated tank, causing this secondary miscible fluid to become dispersed due to the agitation and whatnot. And the salient point is that these physics, particularly the one I just clicked on, it is not appropriate to describe it using a mean flow field. You need the time-dependent three-dimensional physics to resolve this complex mixing process. And that's where these novel approaches, particularly Lattice Boltzmann and GPUs, come to bear, is they allow us to move away from pictures into process simulations. And it's not just closed systems or semi-batch systems, it's open systems as well. Here is a Waukesha pump, pumping fluid, as it were. We can use this to understand the strains and stresses realized in a cell as it moves through the line. Here's looking at some surge tank here. We're examining the residence time distribution and figuring out whether or not we're going to get bypassing, and spoiler alert, we did. We got a lot of bypassing here within the context of this vessel. And again, it's not just single-phase fluids. Here I have kind of a water-glycerin mix coming in through a duct and watching how the turbulent water kind of peels off part of this glycerin into it, thereby producing this von Karman sheet, as we might call it, of mixing at the interface between the two fluids. And so the real takeaway point is this, is that we move to modern architectures and run them on GPUs. We can do things like this in minutes and hours of wall time. None of the simulations I'm showing you here took more than 90 minutes to run. That is, none of these process simulations, as it were, took more than 90 minutes to run on a 2 GPU resource. And that's the big deal, is that these things which are intractable to run using finite volume-based techniques are trivial to run using LBM techniques and GPUs. So what's interesting here, again, is that when we model the time-varying physics, we get better insights. Let me really make this point strongly. So here are 3 agitators inside a square tank. It's purposefully designed this way to induce 3 different mixing regions. So I'll play this here. On the left, I'm showing the time evolution of the velocity, and on the right, I'm showing the time varying. So the left time average is what you typically get when you solve a steady state flow problem. You get this snapshot of the flow field. It's familiar, it's understandable, but it's wrong. On the right is the time varying flow field. Let's compare the two. The time average suggests that at a point right here outside the Rushton impeller, there's going to be this nice parabolic discharge with a maximum velocity right at the center of the blade. That's true in the time average, but that's not what a cell experienced. The cell experienced a strong spatially varying strain in the immediate vicinity of the discharge region. Likewise, the time average solution says that between the impellers, there's this nice, oddly green mid-range velocity. That's not true at all. What's actually happening there is a large range of velocities being realized, as it were. And a cell doesn't see green, as it were, or some sort of mean flow field. It sees this strong spatial variation, energy dissipation, stress, and velocity. That's what's going on inside the tank. Lastly, the steady state solution says that, well, between these impellers, you get no flow. That is, the average velocity is zero, therefore nothing goes there. Wrong. There is a lot of flow going on in the middle of those impellers. Yes, its time average back and forth may be zero, but to assume that the particles there are stagnant or that dye may not intrude there, simply not true. We know there are physics going on there, and when we have a time accurate solution, we can resolve it explicitly. And beyond the fluid mechanics, this informs better process simulation. So here is me adding dye to the top of the tank to predict a blend time or whatnot. And here I see that competition between the different time and length scales inside the system. It takes a while for this dye to eventually migrate through the tank due to this poor mixing configuration. But here I see those heterogeneous structures coming to bear. I see small structures informing local equilibrium. I see longer term structures informing communication between the two mixing zones. These are the physics we're able to resolve when we have a time varying, time accurate CFD solution. We move away from watercolors and into actual process simulation. And that's the real sizzle with all of this. What's kind of neat about this, though, is that when these algorithms, these Boltzmann-based algorithms, are first, derived and developed, this is about, gee whiz, 35 years ago now, they were immediately recognized as being something transformative. That is, when we came up with these things 35 years ago, people knew that these would change how we solve fluid mechanics problem, to the point that it was actually presented on the front page of the Washington Post. Now, I live near DC, so I went ahead to my library and got this microfiche, and it's crazy. Like, how often does CFD make the front page of the Washington Post? It happens once, and it happened on November 19th, 1985. But at the end of the day, they're talking about these algorithms and saying, hey, these new ways of modeling fluid flow are really transformative. We should keep our eye on these. And over the last 20 years or so, as the price of computing has continued to fall, we've kind of fallen into the space now where these algorithms not only are available, but they're what we should be doing. Let me be more blunt here. 20 years ago, it made good sense when I had to spend $2,000 on RAM to just settle for a steady state flow solution. If I had to spend a week meshing a problem, just settle for whatever the machine would give me. These days, the cost of computing is very small, especially as you go into cloud-based HPC and GPU-based environments, which means that the computers aren't the expensive thing anymore, you are. So the more we can unload on the computer using these algorithms that scale well across multi-GPU environments, the more likely we are to win. So again, the problem isn't anymore, oh gee whiz, how can I make this problem fit in my computer? Because computers are really expensive. The problem instead is, how can I maximize the amount of science I'm doing per unit man-hour invested? That's where MSTAR GPU and cloud-based opportunities come into play. Maximizing science and insight per unit man-hour, period. And that's all that matters from an R&D perspective for this case here. And what's important to recognize is not just we're, crazy guys trying to bite our ear here, like about these new algorithms and these new approaches. 20 years ago it was new. 10 years ago it was, got some people's interests. At this point, we have linear feet of textbooks where people are showing how these approaches work, why they're right, how they're so fast, and how we should be using them. So this isn't some sort of zany idea about using GPUs to solve CFD. As the years go on, this becomes the standard, and the literature is exonerating it over and over and over again. Okay, so we spoke a little bit about theory there, and a little bit about a background, where these algorithms come from, what we're doing, some of the history here, some conservation laws. For those who weren't familiar with all this, that's okay. For those who have done CFD, I think you know exactly what I'm talking about when I talk about trying to solve Navier-Stokes equations using finite element-based approaches versus using cellular automata-based approaches. Let's now jump into some examples, as it were, of these digital twins in action, okay? So let's talk about this. When I have a digital representation of the system, here I just have, again, a bioreactor in a stand. What I get out of these tools, again, is not a snapshot. I just go ahead and watch this thing behave. Like here is, as it were, the process going on in real time. So again, if I were in the lab, I might use a laser or LDA or whatnot to characterize the velocity at one point. I might add some dye to characterize the blend time or whatnot. I might use a torque cell to characterize the shaft impeller or whatnot. I might use just visual inspection or video to characterize the vortex depth or whatnot. We do the same thing in digital twins. We characterize data in the exact same way. We predict the time evolution of the torque on the impeller. We put a probe here to measure the time evolution of the velocity. We throw in dye or particles to characterize the blend time. We can use visual inspection here to characterize the depth of the vortex, as it were. We corroborate the tool and use the tool in the same way you'd use and corroborate experimental data, as it were. And that apples to apples comparison makes validation application very straightforward. People see these digital twins and they know exactly what is going on because they're seeing the equipment they see in their lab, plant, and at production scale. And this is why it matters. So here's one of our collaborators. This is in the University of Hamburg in Germany, and they have a huge acrylic tank where you can go there and predict blend time as a function of speed, and understand how different agitation conditions at very large scale might inform your process outcomes. And that's great and that's cool, but it's incredibly expensive. With MSTAR, we can bring that to your computer. That is, we can build these systems and then validate in it off of some number of their cases, and I can send you the literature where we've done this. We can then take what was a $10,000 exploration and move it into a $10 exploration, where we build this model in our digital twin here, and we run it in, I don't know, maybe 30 minutes or so to predict the same physics we would have seen in this much more expensive experimental scale. Now, that isn't to say that experiments are dead. We don't need them anymore. Of course we need them. We need to validate these tools. These work hand in hand. But to think that we can obtain comparable data for orders of magnitude less investment, that's got to raise your antenna, as it were. And that's what these sets of digital twins bring. They allow us to do what might have been prohibitively expensive that makes it practical and immediately accessible. So again, this is me actually doing a blend time study, and I can send you the literature of where we compare this thing apples to apples and show that we can hit it. Carrying on, this is not just for close. Here's another great example of this. This is a 13-chamber CSTR with a mean residence time somewhere on the order of an hour or so. And look at the heterogeneities in the flow field. We have individual agitators inside each cell here, leading to high mixing inside each cell. Superimposed on that fast mixing is very slow transport, slow bulk through the system, as it were, slow bulk flow through the system, as it were. And so being able to capture these heterogeneous length and time scales was crucial for this particular process and application. We had to resolve not only what sort of environment these cells might see as they move through the system, but how long they spend in the vessel and within each chamber experiencing these deleterious strains. So again, the ability to predict these physics in hours on a GPU environment at a cost of tens of dollars, as it were, is a game changer with respect to shutting down a line and dropping $1 million a day trying to characterize this thing in the plant. And that's where the value comes into play. And when you can do this level of fidelity, when you can model with this quality, as it were, it gives you the confidence to do that simulation and get the information you need from it, and then minimize the downtime or actual field testing to just simply corroborate what the code is telling us, as opposed to trying to do all our knowledge generation on a line that's been taken offline. Carrying on, if we're talking about more complex rheologies or whatnot, an API, active pharmaceutical ingredients, these can become expensive. Experiments can become expensive. So the more we can do these mixing studies to predict how different materials dilute and whatnot, and how poorly mixed single-use mixers or whatnot behave, the more we can do that in silico, the more efficiently we can do targeted experiment. Again, this isn't meant to get rid of experiment, but it does make our experiment more poignant and targeted. When we're using the experiment to corroborate the simulation and potentially run a few confirmational cases, that's a smarter way to use our time rather than using an experiment to do a design space, which becomes order of magnitude more expensive. And again, we've been talking a lot about fluids and whatnot, but I don't want to forget the fact that this generalizes to other sorts of physics as well. Here are heating coils being turned on and off to characterize the net flow inside this oven as a function of the applied voltage. There's a lot we can get out of this in terms of the transient physics. And the one on the right here is a broken element, where the temperature is changing as a function of time. The one on the left is working properly, and being able to see these time-evolving physics and model them as they would occur in the plant, that's compelling. Again, the more closely we represent what's going on inside the plant, the more useful these predictions become, and that's what we can do across 3D space and time. And lastly, whether we're talking about, solid systems as well, we can predict, again, what we would see in the lab. Here I'm just tossing a bunch of rocks, as it were, into this agitated tank. I'm playing this in slow motion. This is, I'm clicking this through at 100th of a second, as it were, just because these physics do happen fast. But just watching the interaction between these guys, watching how these particles center, interact with the impeller, as it were, watching how the free surface deforms or whatnot. Admittedly, this is a toy problem, but seeing these different physics come into play, seeing these different physics compete, that's compelling when you can do on your computer the same thing you can do inside your lab. Okay, so we've been talking about some examples of these digital twins in action and a little bit of dog and pony show. Let's talk about why they're useful in terms of being able to do really hard and expensive things comparatively quickly. And this isn't like 10% faster or 10% cheaper. This is like taking a $100,000 exploration and making it a $1,000 exploration. This is like taking a month of simulation and bringing it down to an hour or so. And that's the gain we realize by running on these modern architectures with modern algorithms. Let's talk about why we believe them. Great pictures, compelling pictures, but how do we know they're right? Well, we validate it against experimental data and everywhere possible. Here's an example of a classic problem that came from the DOE, working on some unrelated topics. These were not biopharma projects, but they're tangentially related. Classic problem of flow over cylinder, as it were. Looking at how the velocity varies downstream of the cylinder and whatnot, and showing that we can predict the appropriate decay and recovery of the far field velocity as we move away from this coil. Being able to appropriately predict these the frequencies of the shedding vortices here. These physics, and I'll just editorialize here, you don't get this right if you try to use a rand space solver. You can't get this right with K epsilon. In fact, people tried to recover this experimental data using K epsilon, couldn't get it, and tried to convince the experimentalists they were wrong. Okay, and you can read some of that in the paper here. Foundationally, if you want to get the physics right, you need to model the time-accurate three-dimensional physics appropriately, as it were. And going back to the question of why do we believe it? Because consistently, we can recover data that is measured experimentally, and oftentimes recover data that could not be obtained using simpler approaches. Again, looking at more complex rheology, as it were here. Here's a real neat problem, where I have this shear thinning fluid. Now, the fact that it's shear thinning means that near the impeller, it's going to be more water-like. Near the top of the tank, it's going to be higher viscosity, as it were. So if I'm mixing the system, as it were, the mixing physics would be complex. I'm going to have laminar flow at the top, turbulent flow at the bottom, and that's going to lead to a blend time that may be inconsistent with either fully laminar or fully turbulent systems. So let's watch this in action. I'll add some tracer particles to the top, and at the top I see that familiar laminar ribbon. As I get into the trailing vortex, I start to see all that energy dissipation causing the fluid particles to disperse relatively quickly. I still see some laminar transitional lobes there. I still see some laminar stretching up top. And then how do we validate it? Well, we go straight to the tape. We predict the blend time for a system like this and compare it over and over and over again to published data for these complex rheologies. And again, this speaks to this point about when you're modeling time-accurate three-dimensional physics correctly, you can automatically capture what is a really complex process successfully. I'll say it again. You cannot describe this appropriately using some time average snapshot scheme. You've got to model the physics explicitly and resolve them in real time to get this blending process right, particularly for non-Newtonian fluids. Continuing on, if we're talking about kind of partially submerged impellers or whatnot, or low fluid levels as it were, we consistently compare predicted versus measured blend times over a range of operating conditions. Here's me looking at in some GE Accelerex bioreactor, the 500 and the 2,000 liter vessel at different fill levels. How does the measured versus the predicted blend time, how do they compare as it were? And consistently show across scale, fill level, speed, that these guys agree. We can appropriately predict the blend time in accordance with what is measured experimentally without any reparameterization. We're not changing the model between scales or whatnot. The same physics, the same algorithm is generalized in a way that allows us to predict fluid mechanics at a range of operating conditions and scales. That's compelling. Carrying on, we spoke a lot about single phase stuff. We can generalize this to multiphase physics as well. Here's a bubble column where we're transferring oxygen to an aqueous phase and realizing a reaction. So here I'm showing the velocity field. This is a gas lift system. There's no agitator here. Here I have a sparge bubble, putting gas into the system. Here's the velocity field resultant from the momentum coming from the bubbles. The bubbles are, of course, rising in the tank and undergoing Brayton and coalescence events. In the background here, I have an ongoing reaction where I have the bubbles putting oxygen inside the fluid, and that a reaction producing carbon dioxide. The bubbles are scrubbing the carbon dioxide in real time while depositing oxygen inside the system. The salient point is this: is I'm moving it far away from, well, here's what I think my population balance says my particle size, my bubble size should be, into let's put in some very fundamental physics and let the system evolve organically. And the closer we get to these true transport carriers, in this case bubbles and eddies and whatnot, the more generalizable our models become and the more scalable they become. So that's kind of a cool illustration, just looking at all this competition between different scales and different transport physics involving Lagrangian bubbles, an Eulerian fluid, and the ongoing reaction in the back of the simulation. And again, the salient point is like these guys run in hours in an appropriate HPC environment, that is a GPU environment. And how do we validate? Well, a great thing to validate are things like KLA. Here's me sparging some bioreactor, looking at the time evolution of the bubbles, as it were. This is playing in real time here. And from this, I can immediately extract a KLA and predict an oxygen transfer rate. And more importantly, I can compare that to experiment, but then understand the mechanisms driving it. Understand what's informing KL in terms of the energy dissipation rate. What's informing lowercase a, which is the specific surface area, in terms of the bubble size distribution, the bubble residence time, etc. So I can not only corroborate experiment, but one better, understand the physics driving it, to understand how we can tailor the operating conditions to maximize process outcomes. And that's the utility of a numerical experiment and a digital twin for that matter. I can begin to do in silico the same thing I would do in the lab, and they complement each other very nicely. Okay, so we've talked a bit about the theory and background, where these guys came from, why they matter, how these new algorithms work in some sense, why GPUs matter, and some changes in the computing landscape. I've shown a couple of examples of digital twins in action, just as a dog and pony show, and then I jumped in through about 6 slides of why we believe them with different clients who have used these tools to different things, and systematically compared predictions from the solver to measured data. That's how we validate it. Let's talk about next steps here very briefly as I wrap up. So it's important to note here that there have been step changes, as I said, in algorithms and architectures. Like what we're doing now is like nothing we were doing 10 years ago. And so in your enterprise, if you're kind of doing the same thing now that you were doing 10 years ago, I would invite you to do a loving audit and make sure that you're keeping up, okay? Said again, everything's changed. And CFD and transport physics isn't immune from that, okay? It's not that everything has changed, but we're still running the same RANS codes. If you're still running the same RANS codes, give us a call. In 2020 and beyond, we should be asking a lot more of our modeling. This idea of us settling for kind of a snapshot of the mean flow field after a week of runtime and a week of meshing, that's no longer acceptable. At this point, we should be expecting real-time simulations. We should be expecting real-time process simulations. We should be turning those out in hours or maybe a day if you have a big simulation when running on an appropriate complement of GPUs. We're moving away from calculator and towards digital twin. What I mean by that is instead of getting watercolors here and some colorful snapshot of a system, we're actually modeling processes in real time, which allow us to optimize processes. We want to see what happens when the impeller turns off. Good, you can turn that off. You want to have a time-varying rheology due to reaction? Great. You want to have crystals grow and then see how the crystal size change and forms the suspension characteristics? You got it. When you're modeling time-dependent three-dimensional physics, you move away from snapshots and towards digital twins, which allow us to model processes. And now lastly, it's kind of passing the ball back to the AI and machine learning. The quality of your AI, the quality of your machine learning is only as good as the fitness function going into it. Said again, if your fitness function, if your super exotic AI algorithm or really clever machine learning algorithm is using a suboptimal mechanistic model, well, it's only as smart as its dumbest component. If you're going to go through the investment of trying to learn how to do machine learning and AI and do that well, you need superior physics under the hood in terms of feeding those models with appropriate data. And that's where these tools come into bear. Okay. With that, I'll close. Thanks so much for giving me a chance to kind of speak to these points, and reach out to me directly should any questions come up in the midst.
Thanks, John. So next, I'd like to further explore large-scale design exploration. So here we have a design simulation workflow that many of us are very familiar with. So here you've got a physical simulation that you're going to run on some hardware, and you have inputs describing that physical simulation or algorithm, along with the outputs that you desire to be able to iterate in your design process. And so here in the middle we have black box of physics solver or statistical model. And there's been a lot of technology that's gone into, making these solvers very representative of physics, very high fidelity, and run, very efficiently on the available compute hardware. But of course, in order to make any use of these tools in a practical design cycle, we have to be very conscious of the horizontal axis here, time. So these simulations, oftentimes we're still limited in our ability to model based on the time that we have. And so a lot of technology has gone into, well, how can we throw more computing power and improve the solvers to be able to solve a higher fidelity or a longer duration simulation, if you will, given the same time constraint. And MStar CFD is a perfect example of using a modern cutting edge compute hardware with new algorithm design to be able to achieve much faster simulation time with even a smaller amount of computational resources. Now the challenge here goes, what happens when you want to look at multiple iterations or perturbations of your design, or look at different design points? And so here I've depicted that where now we've got this vertical scale where not only are we looking at a single linear workflow of simulation, but now we want to look at maybe multiple different input parameters that define that simulation space. And so we have a couple options here. One is to take a simulation that already leverages a large computing footprint and run two of those or three of those in parallel with each other. And so in order to do that, maybe we reduce the fidelity of our simulation or we acquire new hardware. And so this is kind of where we are currently in terms of design exploration. Now, this isn't all bad. Of course, this gives us the ability to look at a broader spectrum of the design space and ultimately get information like a design surface where you can see trends and have, inform your design cycles more efficiently. But what if we remove the vertical scale altogether and say, how would your design exploration look if you had nearly unlimited scale in terms of the computational resources? Well, Rescale's vision of this is it might look something like this. You might have, more than a few input points, design points. You might have an entire input space defined by some input matrix. And you might be running multiple different simulations using different physics solvers, different models, but also at different fidelity. And on top of running, hundreds or thousands of those simulations in parallel, we realize these simulations in the time domain may not also be linear. You may have a low fidelity model that informs a higher fidelity simulation subsequently. And so, when you remove the computational burden, then of course we still have to fit within a time space, but we're able to really explore the design space much more thoroughly and ultimately arrive at a more optimal solution. So when we consider these complex and highly parallel computations, we can look at them in a broader category of massively parallel computation. And as we discussed, this type of workflow and scale enables design space exploration, and this could include high throughput simulations where you need to run hundreds of thousands of simulations that maybe only require a single CPU for a few minutes, but just the sheer volume of the number of simulations required requires this large parallel capacity. Multi-step workflows, both prescriptive but also where the upstream component of the workflow informs the subsequent analysis. Data processing and analytics. This could be, from image processing to statistical, sampling of large data sets, where you want to span that out over, hundreds of processors. And then finally, data generation for training and testing machine learning models, running your physics simulation, hundreds of times over a design space to produce training data for an AI model. Now, what are some of the challenges? Well, first, computational scale. It might have been easy for me to remove that vertical, axis on the PowerPoint chart, but in reality, amassing hundreds of thousands of CPUs and GPUs requires an infrastructure and an orchestration engine that is not straightforward to implement. Secondly, when you talk about running parallel, hundreds of parallel simulations and also multi-stepped simulations, you need some kind of an orchestration engine that allows you to compose that workflow, allows you to monitor the workflow, and then also access the results in a convenient manner for collaboration, repeatability. And then finally, each component of these multi-step workflows, or even each parallel thread in a massively parallel computation, may reflect its own unique software-hardware pairing. You may be running CFD and MPI on hundreds of GPUs, or maybe on a handful of you may be running CFD in across hundreds of CPUs with MPI, or maybe just a handful of GPUs. You could be doing molecular dynamics where you have high RAM requirements, and so each component of that workflow needs to be reflects a unique installation of a physical simulation tool along with the correct hardware for that simulation. Next, I'd like to discuss some emerging trends in AI and machine learning. These are just a few of the examples of the many different use cases that these statistics-based models are benefiting the biomedical industry. One of them that is particularly interesting, and you may have seen in social media or in the news recently, is surrounding protein folding. And so, just recently, Google's DeepMind released AlphaFold 2, which is a neural net that is able to predict protein folds given an amino acid sequence chain. And it's able to do that at an accuracy that far exceeds previous attempts. In fact, if you look at the last two models produced by DeepMind, which reflect the first large-scale deep learning attempts at this problem space, you can see in the chart here the impressive accuracy gains attained by these models. And these models are informed by experimental data, but also can be informed through physical modeling. They require a lot of data. I think in this particular case, they trained it on over 170,000 different protein molecules, but then also require a large computational resource to train the models. In this particular case, since it was performed at Google, I'm sure they used tensor processing units, but it's equivalent to 100 to 200 GPUs running for roughly 2 to 3 weeks. So we're talking large scale usage of very new compute architectures. Now, I won't claim to be an expert in all of the applications of AI and machine learning across the biomedical industry, but I will say that with regard to the science and engineering communities, the application of these statistical tools is fundamentally different in terms of applying them to engineering and science workflows than it is for, say, advertisement and search that you might have on the internet. And so there's several different things that make these models complex. First of all, the data sources. Of course, we have experimental data that require a large amount of processing. But I think also we have the means to produce and amass data from sensors embedded within our physical devices as well as our physics-based models. And so these machine learning models are really there to be an aid in the design process. They certainly do not replace the use of testing and physics. And so they need to accompany alongside our physics simulation computational environments. And so yet again, as we've discussed, here we're adding additional complexity to not only the software that you need to run, such as say TensorFlow, Keras, Python, other machine learning frameworks, alongside of your molecular dynamics and CFD and crystallization type software, but then the underlying hardware becomes very complicated as well. CPUs and GPUs and MPI implementations and network interconnects. And then finally, when you think about these very complex workflows, both in the guise of AI machine learning, but also in large scale design exploration and digital twin, you start to realize that collaborating in such complex work environment or computational environments, and workflows requires something a little bit more than, say a laptop or even a command line based compute cluster. And so things like APIs and web interfaces for visualizing the workflows, and even dashboards to be able to showcase the stages of compute and other metrics of that nature become important. And so that leads me to the final topic I wanted to discuss today, and that is just surrounding how do we address some of these HPC challenges to to realize some of these trends that we see in computation and digital R&D in the biomedical world. And so we've already talked a lot about being able to amass computational resources at scale, being able to host software on the correct hardware for particular analyses. But in other things that other challenges that exist today are how do we manage the cost? How do we provide the computational resources when the demand is there without oversubscribing? And how do we collaborate not just within an organization but across organizations as well? What are the infrastructures needed for that? And then finally, realizing that these trends are accelerating and are occurring at a very rapid rate, how do we stay on top of these new trends and harness those new capabilities? Rescale addresses these challenges by offering a modern HPC experience that, simply put, provides a single platform that hosts any scientific or engineering application on any hardware infrastructure. We currently have over 600 different simulation and engineering tools available on the platform that are tuned and optimized to run on a variety of different hardware infrastructure, including the public cloud and your on-premise resources. We marry the application and infrastructure layers with an intelligent control plane, which provides an easy-to-use interface for workflow orchestration and automation, but also provides intelligence surrounding software and hardware combinations, as well as pricing and budget intelligence. Overall, the Rescale platform is the modern HPC experience to accelerate digital R&D in the scientific and engineering worlds. Thank you again for the opportunity to present at today's BioIT webinar. I'd also like to extend an appreciation to John for co-hosting with me today, and encourage all of you to visit us at rescale.com and reach out if you would like further information on Rescale's modern HPC experience.